Hello, my name is Brock Lemires, and I will be your instructor this summer in EELE 367 Logic Design. In this video, we're going to go over the course and discuss the logistics of how it's going to look, what you are going to do, how you're going to turn in assignments, and just the overall programmatics of the summer. And then what we're going to do is I'll give you an overview of the class, and then I'll give a little bit of background on myself as the teacher and also the author of the textbook and the voice and hands that you'll see and hear on the videos.
So let's begin with what this course is all about. And to do that, sometimes it helps to take a look at the prerequisite for this course to put it in context of what we're trying to accomplish. So the prerequisite is a course in digital logic circuits. That could be either EELE 261 at Montana State or an equivalent class at another school. But the goal of that was to start looking at the basic building blocks of a computer. And so we're looking at the hardware and we're looking at the very low level. So like AND gates and OR gates and stuff like that. So very, very low level. And to do that, we had to start with looking at like, what is a digital signal to begin with? What is this whole thing of ones and zeros, and how do we interpret voltages to be that, either a logic high or logic low? Then we said, well, if we're messing around with ones and zeros, we got to know number systems, so we got to understand the binary number system and how to perform arithmetic and how to represent information with that. Then we had to look at the digital circuits. So if we're going to build circuitry that manipulates ones and zeros, we have to go down and look at what is it? What is an AND gate? What does it really look like? What kind of voltage levels does it use, power supplies, etc. And then we looked at, well, okay, now I'm going to do combinational logic design, which means if somebody gives me a truth table, I need a process to synthesize the circuitry. And so we looked at K-maps and build, and minimization, logic minimization, and sum of products, product of sums, architectures, and all that sort of stuff. But it got us to the point where we were able to take a functional description of a circuit in the form of a truth table, and we were able to actually create a gate level schematic and implement that on a breadboard. And that was pretty cool. But then we also said, geez, man, this is really tedious. The designs get big really quick. So we introduced VHDL, a hardware description language, which allows us to basically describe the circuit functionality we want in text, and then allow a tool such as a synthesizer to actually crank through and create the gate level design for us. And the reason that was really neat is because we could actually simulate the functionality prior to actually building the circuit. So we could figure out if we had errors in our logic. So then we use that to explore larger combinational logic circuits, such as MSI logic. So that's like decoders and multiplexers. And then finally, we learned about sequential logic, which is building finite state machines. And that is that circuitry that produces outputs based upon where you are in terms of the inputs and where you've been in terms of the inputs. So we had this notion of storage in the form of D flip-flops, and the D flip-flops were able to track history by having a sequence of states that represented where it's been. Okay, so then that brings us to this course, which is called Logic Design. And so what is logic design about? Well, we're still looking at the basic building blocks of a computer. The only issue is that to get to the end where we can actually build a computer, the next ones are going to be pretty big. Okay, so it's no longer, well, should I use VHDL or should I use a K-map? The answer is you're done with K-maps, okay? So we're now going to use a hardware description language for everything going forward. So the next modules, we actually are going to do module 8, 9, 10, 11, 12, and 13. Now you're like, why is you not starting with module 1? Well, actually, this is a continuation of my book, Introduction to Logic, Circuits, and Logic Design. Notice that the first class was Introduction to Logic Circuits, and this class is called Logic Design. So that's why where the title of the book came from. It's the two classes that I teach put together. So module 8 is chapter 8 in the book. And so we immediately start with saying, well, we learned a little bit of VHDL, but I need some more advanced techniques to model big stuff. And so we go to VHDL part 2. And this is where we look at things like a process within VHDL that allows us to trigger signal assignments instead of just having them happen immediately as soon as there's a change on the input. And that opens up things like if-else statements and case statements. And we look at how we can build finite state machines with that. And we look at how we can model all different types of different circuitry. So then module 9 is where we go back and we start looking at it. Let's go ahead and model some of these larger combinational logic circuits and even sequential logic circuits using the techniques that allow us to go big. So some of these techniques that come from Module 8 VHDL Part 2. So this is where we go back and we're using if-else statements and case statements to build big decoders and stuff like that. Then we go and change gears quite drastically, and we look at how to build a memory system. So we no longer use D flip-flops to store information. We're actually going to build memory arrays. So we look at the technology and the architectures used to build ROMs and read-write arrays, and then we build that in VHDL, and it turns out that these are absolutely synthesizable. And then we turn our attention very quickly to programmable logic. So since we are now going to be implementing everything on the FPGA, we already are doing that, but we've kind of glossed over what it is. We're just like, don't worry about it. It's just a programmable logic device. Put your VHDL on there, and trust me, it works. Well, now it's time. We can't do that anymore. We need to be owners of the hardware. So we actually go and look at what is an FPGA. And to do that, you have to kind of look at what was the history of programmable logic that led to the development of an FPGA. And once you get to that point, now you're sitting there going, okay, now I'm getting good at digital design, because I'm not just throwing VHDL down, hitting synthesize, and hoping it works. It's like I know where the gates are going. I know they're going into lookup tables on this FPGA, and I know what an FPGA is. Then we turn our attention back to arithmetic circuits. And so this is where, instead of using like combinational logic, explicitly to do an add, we start using the plus sign, and we start using the minus sign, and we start using, higher level modeling techniques to implement these arithmetic circuits. And that then culminates with the granddaddy, which is Module 13, where you will build an entire 8-bit computer in VHDL, and you will program it by putting opcodes and operands in the program memory and running it. This module is the culmination of both classes, where you have learned all the pieces that go into a computer system. You know how each works, and then we bring them all together and learn how to build the most ubiquitous technology there is on planet Earth, which is the microcomputer. And so this hopefully will be the light bulb moment that really brings everything together that you've learned in logic. And you understand, it's like, wow, I've written Hello World and I hit compile and it works, and I have no idea what is going on in the hardware. Now you're going to be like, wow, I understand what the hardware is doing. So before we get into the logistics of the class, you must be wondering, well, who is this guy who's going to be teaching me about these building blocks? So I am a professor of electrical and computer engineer at Montana State University. So I am physically located in Bozeman, Montana. And I got my bachelor's degree from Montana State back in the 90s. And then I went to work for Hewlett-Packard, where I designed electronic test equipment for 8 years. And I was a digital hardware designer. So I did FPGA design, printed circuit board design, acquisition system design. And so all of the circuitry that I'm going to be teaching you about is stuff that I actually use as an engineer in industry. And so this stuff is real. It's not just make-believe. You will actually use this stuff. And so while I was working at Hewlett-Packard, I decided to go to graduate school. So I went to, I got my master's degree at the University of Colorado in Colorado Springs. And then after that, I started teaching as an adjunct instructor, classes on embedded systems at University of Colorado in Colorado Springs. And after a couple of years of that, I decided that I really liked teaching and I really liked being an electrical engineer and a computer engineer. So I decided to go back to school and get my PhD. And so then I continued working and going to school, but this time I was going to school at the main campus, University of Colorado in Boulder. And so then after years went by and I ended up getting my PhD, and that allowed me to become a professor. So in 2006, I came back to Montana State, and I have been a professor now for nearly 15 years. And what I do is I teach and do research in the broad area of computer engineering and digital systems. And so I'm showing you my website right here just to kind of highlight some of the things that I do. So the classes that I teach are like Introduction to Logic Circuits, obviously, both at the very low level all the way up to senior and graduate level, digital system design and high-speed digital system design. And then I do research on, using embedded systems to solve problems and also coming up with novel computer architectures for various applications. So my main work, if I come out to my research over here, my main work has centered around trying to exploit these programmable logic devices to create real-time adapting hardware that can recover from faults,
or give you better performance in real time. And so most of my work has been funded by NASA. I currently have a project right now where I'm building a computer that's going to go to the moon in 2022. I've got we actually have this computer that we've invented called RAD-PC that uses an FPGA and can react to ionizing radiation that causes a normal computer to crash. And so we've developed this computer and we're going to fly it, or we actually have 2 small satellites in orbit. One of them is called RadSat-U. This is a picture of it right here. This is its launch back in November of 2019. I'm standing in this crowd right here with my students watching that go off from Wallops Flight Facility. Here's a picture of it being pushed out of the International Space Station, so it's in orbit right now. We have a second satellite that's up there called RadSat-G, and these things are about the size of a loaf of bread. Here's its pictures of it. It's launched at night, being pushed off the International Space Station again. And then we do all sorts of other things like balloon flights to try to test this computer in various environments. We've had it on the International Space Station. Here's a version of this computer, RAD-PC, being installed by an astronaut. And then we've done everything from flying on sounding rockets to weather balloons. And so anything and everything to just kind of test that technology. So what my background brings is I have a degree, a PhD in electrical and computer engineering. I've also worked in industry using this stuff. And then I also do research that really takes what I'm about to teach you and actually implements it in applications that can kind of advance computing technology.
Okay, so now let's look at how you actually engage in the course. So everything starts with what we call Brightspace, and Brightspace is the learning management system for our course, or the website. And the website that you use is ecat.montana.edu, and it'll redirect you to like ECAT 1 or ECAT 2 or whatever. But when you log in with your NetID and password, what you'll see here is this main screen, and then if you scroll down to your right, you're going to see the courses that are active, and what you'll find this logic design class right there. So if you click on that, what you're going to see is you'll see the announcements, and each week we'll have a little announcement here that kind of shows you, just a reminder of what we're going to do, even if you needed it. And so right here, this is the week 1 activities. Now, picture the book, and you read through this, and the first thing that you see is you need a portable lab kit. So if you're watching this video and you don't have your portable lab kit, you need to go get it. So go to the ECE office right away, or contact me and give us your address so I can ship it to you. Okay, so remember, we're starting at chapter 8 in this book, and so we actually start right away with module 8. That's why we don't start at module 1. And during the first week, you'll see that there's actually assignments that are due, and some are going to be due the first Wednesday of the class. Okay, and then after that, we get into the cadence of everything's due Wednesday at noon of the following week. Okay, so then you come in here and you see across here all the tools within Brightspace. Content is where you'll always start. I have pages for every module. So you're going to have content as the big one. You'll also click on grades to see, what your current grade is. Everything else like quizzes and assignments, those are linked in content, so you never really need to mess with those unless you just wanted to see what all the quizzes are at once. But if I come down here, you can click on this link right here and it'll take you to the first page, or I can go into content. Let me show you that. So right here, notice that I have a page for everything in the class. So you have course information, module 8, all the way to 13, and there you go. So if I click on the first one, you'll see like a snapshot of the syllabus, but I do it as a page so that you can have the links, okay? So for example, this one right here, it starts off, here's the course syllabus, course overview video that you're watching. This one is with my voice somewhat restored. And then there's a course overview quiz to get you kind of going, earn some points, and just show that you actually watched this video. And then you see, here's the course instructor. This is all just snippets from the syllabus that we'll go over in a second, but it shows you links too. So obviously, here's my contact information, but a big one is the WebEx room. So this is the room you would ever use if we wanted to do a video call. And then here's Charlie. So Charlie's the teaching assistant, and this is the person you're going to be in contact with the most, because Charlie is going to do all the grading and help you with all the homeworks and the labs. And so since he's doing the grading, you want to make sure you're in contact with him. He's got a WebEx room right here. He's an email address. The way you do it is you email him, set up a time if you want to meet, and just do a quick WebEx. And you'd be surprised at how efficient it is. We've learned over the years that it's like sitting at a computer, you can tilt your camera down, show your circuit, show your code, share your code, and we can actually help you just like we were live. And so it's taken a lot of years. but we've been there. So the primary mode of communication in this class is email. Okay, and we'll try to email you back right away within 24 hours. And since we're going to be doing email, I give you this professional email etiquette guide to kind of show you how you should be emailing. And it just helps the email be more efficient. And if you follow this and then do a little assignment at the end, I'll give you some extra credit. So we get down to here. This is in the syllabus too, but we'll cover it here. First thing you need to know is you need a computer that runs Windows. Okay, we're going to be using design software. It's Quartus and Model Sim, and it doesn't run on a Mac, and there's just no way around it. So if you have a Mac and you can dual boot, go for it, but I can't help you with it because I don't use a Mac. All engineering tools run on Windows now or Linux. So if you're using a Mac and you can't dual boot or you don't have access to a PC, you should drop the class, honestly. In fact, just drop out of engineering, because if you're holding on to this idea that a Mac's going to help you, that you're going to some way figure out a way to get the tools to run on a Mac, they just don't. Okay, I've been doing this for 25 years and they don't. Every once in a while you'll see one that does and you think you have hope that you can use a Mac, and the answer is you can't. If you want a Mac as your personal computer to do other things on, that's fine, but you got to have a Windows machine to run the engineering tools. Here's the book. Here's a link to buy it. Don't buy it in the bookstore. They're always more expensive. You can get a hard copy through Amazon right here. So if you click on that, you'll be taken out here. If you're a college student, you get like free shipping and all that sort of stuff. And, it's relatively inexpensive. But then the big one, Digital Logic Portable Kit. If you've taken the prereq for this class, this class is all about FPGAs. Every lab we're going to do is with an FPGA. So you're going to be writing VHDL, you're going to be synthesizing it with Quartus, and then you'll be demoing it with a camera and screenshots. And so you'll show you the FPGA board, you'll upload the video, upload your VHDL code, and then that's it. But you got to have this Digital Logic Portable Kit right now. So make sure that you get that thing. Okay, so now this is great. Let's take a look at the syllabus. Okay, so I'm going to look at the syllabus, and this is the main thing in the syllabus is the schedule. So every time you go to do anything, you want to be looking at the schedule so that you can see what you're actually supposed to be working on that particular day. And so let's take a look at this. Description, we already talked about. The objectives, every module has a learning objective. Instructor, teaching assistant, that's Brock, that's Charlie, contact. We start on the 10th of May and we end July 30th. 12 weeks, fully online, asynchronous, do this from anywhere on the planet, as long as you have the lab kit. And here's the required materials we just talked about. Prereqs, you got to know what an AND gate and an OR gate is, and you have to have touched the FPGA. If you haven't, you should review on how to do that. Course website showed you that. Office hours, there's no office hours. We're just always here. Just email us and we'll log in. Distribution of grading. So notice homework, there's 1,000 points possible. Homework's worth 150. Labs are worth 450. So all the learning happens in the lab. End of module quizzes, to keep you honest, you're going to have these end of module quizzes worth 200. But then the final project is worth 200. The final project is actually building an entire computer system in VHDL and implementing it on an FPGA. So actually, in reality, 65% of the class is a lab, and that's the way it should be. This is a skills course, right? When you're done with this, you're going to be able to bang out designs. Okay, this isn't just like writing on a whiteboard. This is about learning how to program and design hardware. Okay, grading, I grade straight, 90, 80, 90's an A. I don't give minuses because they don't have an A+, and it's always irritated me. It's like if you get a 90%, you lose points because you get an A- on your GPA, but you can't, if you get a 99%, you don't get an A+. You don't get a 4.2 for this class, so it's always irked me. So no pluses. I reserve the right, of course, to do whatever I want and apply pluses and minuses. I need you to pass 70% of the labs. In this class, since the labs are so heavy in the grading, it's not a big deal, but it's some classes you can just plunk in multiple choice homework solutions and pass the class. This is not one of those classes. You're going to be coding VHDL. Academic policies, don't cheat. But I want you to collaborate if you can. Okay, so the difference between cheating and collaborating is where you're working with a group of people or a partner, and you're sharing ideas and you're looking at each other's code and you're asking for help on each other, but you're both doing your own work and you both turn in your own work. Cheating is where you turn in somebody else's work. Okay, in this class, everybody has to type their own VHDL. Even if you're working in a group of people, you have to upload your own VHDL that you typed in. Watching somebody else type, you don't learn. You got to type the VHDL in yourself, okay? So that's the difference. Course components, you're going to read, you're going to do instructional videos. This is how we transfer the content from my brain to yours, or from the collective engineering community into yours. So I designed the course first, then I wrote the book. And so everything in the book we cover. Okay, so we're going to march from chapter 8 all the way to chapter 13. We're going to do every single section in there. And you can learn everything with the book. You can also get some instructional videos. And then obviously some people like videos. So I made videos that match the book. These two are the same information. Okay, so if you're a reader, you got the book. If you're a video person, you got the videos. If you like the videos with a reference to the book, go for it. The book has a lot of examples in it, like that help, like show you snippets of code. So it's pretty useful. Every section that we cover in the book is going to have a graded homework. Now the graded homeworks are going to be in the form of a multiple choice quiz in Brightspace, or by doing a VHDL simulation. So you'll type some code, you'll simulate it, and you'll take a screenshot of your waveforms from the simulation, upload those, upload your code, and we grade it. Okay. Multiple choice quizzes. The key with these is they have a deadline, and you can open them and work on them as long as you want up until the deadline. So you can open them, enter some questions, save it, leave, come back, do it. Okay. That's different than end of module quizzes. I'll jump down here. At the end of the module quiz, you're going to have a quiz. It's technically a quiz, but they're timed. Okay, and the difference is that once you start them, the clock starts and they go away at the end of the timer. So you're either going to have 30 minutes, 60 minutes, or 90 minutes. These quizzes are to kind of emulate in-class exams. Okay, so they're supposed to be a little bit more high stakes because you don't have enough time to like look everything up. So that's the difference. But they're both administered in the same tool, like a homework quiz versus a module quiz. Lab assignments. Oh baby, this is where you're going to be doing laboratory assignments all the time. Okay, you got your FPGA board. You're going to be writing VHDL, flashing lights, clicking buttons. Life is good. Final project, we're going to build up a full-blown computer. This is going to change your life because it's the greatest thing that's ever happened so far in your life, I'm assuming. You're going to build a full computer. You're going to program it with ones and zeros. It's going to execute instructions that you design. Life is good. Okay, here's the schedule. This is where every time you log in, you want to pull up this syllabus and look at the schedule because this tells you everything you're supposed to be working on and everything that's graded and everything that's due. So for example, in week 1, we're going to be doing a course logistics, and there's actually a homework assignment. It's worth a point of the 1,000, and it's due this Wednesday at noon. Then you're going to move to module 8, and you see that you're going to do section 8.1, 8.2, 8.3, 8.4, and you're going to do a lab. Okay, they're all worth varying points. Notice the labs are worth way more than the homework. Notice that some of the homework is worth way more than other homework. That's because every time you do a VHDL simulation homework, that's worth a lot more than a multiple choice quiz. Okay, so you see that the big points are associated with typing VHDL and simulating it, and then writing VHDL and synthesizing it. Notice also all the deadlines are Wednesday at noon throughout the entire course, except for the last week of the class. So you're going to get into a rhythm. I want you to have an assignment the first week of class just to show that you're engaged and can log on. So I have these 2 really light assignments. They're due Wednesday at noon. That's it. After that, you're going to work on assignments, and everything you work on is due the following Wednesday. So you look at the week. Here's what I'm doing this week. It's due next Wednesday at noon. That gives you the chance to have the weekend and ask some questions next week. But in general, if you stay on track, you won't. If you just stay on track, you'll get into a rhythm, and this class will go very smoothly. We work through all the modules. We go through sequential storage, sequential modeling, memory, programmable logic arrays or FPGAs, arithmetic, and then look at this. Weeks 10, 11, and 12, big red. You're designing a computer. I give you a couple homework problems, multiple choice quizzes just to get you terminology set up, and then you start hammering this out. It's worth 200 points. It is worth 20% of your grade. It is cool. It's such a big project. I break it up into sections, so you actually have there's 4 parts to it, and that helps from instead of just having one big deliverable. But this is every time you log in, you want to pull up this table right here and look at it. If I ever update it, you'll notice the date right there, and that's that. Okay, so now that's the syllabus. Let's look at how you actually engage, or actually how you access the content. So if I come over here, I can click the next page, or I can go up to content and look at this. Here's what a content page looks like. Every module has its own content page. The schedule you cover the module comes from the syllabus. So just because you have it's not like 1 page per week. It's look at the table in the syllabus and then come back and look at this. Every module has learning outcomes. We don't do something for nothing. We do it because we're trying to learn something specific. Then you get to the activities. Section 8.1, 8.2, 8.3, 8.4. I told you, we're going to cover every section. 8.1, it's going to look very similar, the process. You have read, watch a video, do a homework. Section 8.2, read, watch multiple videos, do a homework. Section 8.3, read, watch a video, do some homework. Section 8.4, read, watch some videos, do some homework. You just repeat. After we get enough of these sections under our belt that we can do something cool, like do a lab, then you have a lab, okay? In this module, it just turns out you did 4 sections in a lab, and then you do this description. I have overview videos of the lab, then you upload your stuff to the assignment folder. If I go ahead and click on the description, it downloads this massive PDF. You only need to download this once. It has all the lab assignments in it. But I'll just kind of show you like what a lab is going to look like, the type of stuff that you're going to be doing. You're only going to be doing FPGA labs. So if I go to 8.1, let's jump down here. You're going to be, look at this. You're going to be checking out one of these FPGAs. There's actually 2 different types of manuals that there's 2 FPGA boards that you can use for this class, one or the other. And we're using the DE10 Max, okay, or DE10 Lite. And it looks like this. It's got LEDs, it's got switches, it's got buttons, it's got 7-segment displays, and it's got I/O headers. And here's the big dog, FPGA Cyclone 5 from Altera, now bought by Intel. And this is what you're going to be. Doing. Okay. So this is you'll be given a description of what the circuit you're going to build. You'll look at, like I point out where it's going to come in. You do all the design. You download everything, life is good, and you upload it to the assignment folders. I highlight in red what is actually needed for the deliverable. So like in this one, if you look at the lab assignment, I always start off by, as you would imagine, sorry for the motion sickness there, learning outcomes, the parts you need, deliverables. So you have 2 deliverables for this, and as you walk through the things, in red you'll notice, oh, this is what you need for deliverable number 1, this is what you need for deliverable number 2, and life is good. Okay, and at the end of Module 8, there's the module quiz, and now you say, it's timed. Let's take a look at Module 9, just to repeat the behavior. Learning outcomes, and here's your activities. Notice I do section 9.1, 9.2, then I do a lab. Well, that's cool. Then I do 9.3, then I do a lab. Then I do 9.4, then I do a lab. Then I do 9.5, then I do a lab. Then I take the end of module. This module 9 takes 3 weeks. How did I know that? I went to the syllabus and I said, oh, look at this, 1, 2, 3, 4. It actually took 4 weeks. Life is good. Okay, and that, my friends, is how you actually do this. If you had a homework assignment that's a multiple choice quiz, you click on it, the quiz tool comes up. It's like, oh, okay, I do my quiz there. If it's one that's a VHDL, what you'll get is another page that shows you the exact assignment, and I give you some tips on like what the thing should work on. Okay, so that is it. That is the course. That is how you access. That's what we're here to do. That's who I am. That's how the schedule we're going to do. Those are the logistics of it. This course, when you do that computer, I'm telling you, it's going to change your life because you're going to finally understand all the technology that's around you. It's a light bulb moment. And I look forward to working with you this summer. So that is it, and good luck.